All right. So we have every processor that we are having right now is essentially a pipeline processor, and but however, we hope that the CPI could be always one. However, there are three different types of pipeline hazards are preventing us from getting CPI equal to one. They are structural hazard, control hazard, and data hazard. And we have been talking about solutions to structural hazard and control hazard earlier this week. And yesterday, we have been talking about how to address the data hazard through hardware technique called data forwarding. And the idea of data forwarding is very simple. So for example, it's essentially just having wires that connecting to your functional units as the input. And whenever your processor feel, well, this is the input from other functional units is probably the right one to fit into the functional units, then that's when we are starting to do data forwarding. And as you can imagine, if you want to support data forwarding, you need to have very complex wires that would actually make your hardware design wiring very complex, right? And another question which we later raised is that why can't they work at the same time, right? Because if you look at, well, we have been using pipelining to have all the functional units available all at the same time. However, one part we haven't fully explored is that the fact that we have multiple functional units like branch prediction units, ALU, complex ALU, and memory. However, if we have an instruction that we want to execute, so far the best is that we can only use one of them, which is also a waste of your hardware resource, right? Imagine like a lot of people yesterday were complaining about how inefficient a DMV is or driving school is, right? But the fact is that, well, if you have a service model that, okay, I have a lot of different affairs that the DMV has to deal with, for example, the driver's license, the plate, whatever you can imagine, but whenever there is one being served, other people are just idling, right? So that's very inefficient. And that's what we exactly are facing now. So to make that more efficient, the naive way, or say the most intuitive way, is that we just widen the bandwidth of fetching data, the bandwidth of decoding data. So turns out this solution is called superscalar. So with superscalar, it's not an idea that we increase the number of functional units in a pipeline. In fact, we are trying to enlarge the front end of your pipeline by receiving more instructions at the same time and being able to look into what an instruction wants us to do at the same time. So with superscalar, we are so happy that, okay, what if we try this pieces of a code, which is a loop, right? And in the last lecture, we look at this loop and we figure out that, well, even with superscalar, it still takes a lot of time. And in many cases, we are just wasting our hardware resource, right? So right now, what you can see here is that although we have functional units like this, and like ALU branch and like memory units. However, the best we can do is only have, like 2 of the instruction at this cycles in different stages in the memory pipeline. However, the ALU are totally wasted, right? And so superscalar has its own issue in a way that, well, we still have trouble filling in, make everyone busy, right? So we were talking about we can use compiler optimization to optimize the code. However, it still has implementation, right? So now today we are going to continue our discussion on the issue of superscalar, and we are going to tell you how can we make superscalar more efficient in a way that we can improve the throughput of a superscalar processor. So here I am expanding the same pieces of a code because a lot of you might think, okay, with superscalar processor, we just don't have sufficient amount of instruction, right? So now that's assumed, well, because if you remember the code that we have, right, most of the time, that kind of code, you will run the iteration for time over time, iteration over iteration. So we duplicate the instruction for 3 times, and let's see what's going on, right? So what we were having is that, okay, everything we need for instruction 4 is ready here, but we cannot execute instruction 4 because instruction 3 was actually blocked by the result of ECX is not coming yet, right? And then some of you might be curious about, okay, so previously we don't fetch instruction 6 after instruction 5 because we are having the issue of there is a branch, right? So now, and some of you might argue that, okay, professor, you mentioned that the branch prediction are doing a fairly good job now, right? So why don't we assume the branch prediction is in place, right? So, and in fact, it's very unrealistic that you assume that you have a processor without branch prediction. Okay, let's make the branch prediction in a picture. So with the branch prediction, we can fetch one more instruction, right? Instead of just fetching instruction 5, because now we know, well, after instruction 5, there could be one instruction and we predicted that one. So we predict number 6, which is another instance of this move L instruction, right? But after that, right? After that, because there is a data hazard between 3 and 1, so 3 cannot make progress, and everyone is blocked because of the fact that 3 has data hazard with instruction 1. So it turns out, even though at this moment I can fetch 6, I still have issues of fetching like 7 and 8, even I have very good branch predictor, right? So it turns out everyone is still stuck in here until instruction 3 resolve its data hazard with instruction 1. We can start making some progress. But again, if you look at other instruction, there are still hazards that prevent us from making better progress. So it turns out, even though I unroll the loop several times, right, with very good branch predictors, I still see a lot of waste in hardware resources like this, right? So every time when you see this part of the pipeline has an empty slot, you know you are wasting some resource, right? So this is still not ideal, right? But if you look at the code carefully, right? So some of you might argue, okay, because 3 is waiting for 1, so there is no way we can make progress. That's true, right? But if you look at this pieces of a code, right, like for the move L instruction here, right, it's actually depending on RDI, and the RDI value is updated after instruction 2 finishes execution, right? And with data forwarding, theoretically, after instruction 2 has finished its job here, the next cycle, you should be able to get an up-to-date value of RDI, which should allow instruction 6 to start here. Agree? However, we cannot, because we have to execute instructions in order for now, right? So that's part of the efficiency, right? So in DMV, a lot of cases you are, or in a driving school example, I like that driving school example, by the way. So in a driving school example, right? Sometimes you might think about what the people in front of me is doing, right? Like, how come that person doesn't have the data available, documents available, but still blocking it in the line, right? Or okay, the person in front of my line, that in front of me has document not available, and in the meantime, what I can hear is that, okay, that person is not trying to figure out where to get his document, still like looking the Instagram or whatever, right? Not doing anything. So okay, gosh, I'm ready. Why don't you guys send me to the front now, right? So that's exactly the problem that we are facing now, right? So because you have to execute instructions in order, so there are cases where, well, because there are hazards of the front instruction in front of you, so you cannot start executing. So turns out, right? If you look at that, right, that's actually not a good model. So in fact, if we can forget about the order of your instructions, right? If you can forget about the order of instruction, what do you actually need to have an instruction execution? So 3 criteria, right? First, whenever the instruction is decoded, right? Whenever the instruction is decoded, my processor can know what the instruction really want the processor to do, right? That's one criteria, very basic criteria. And the second criteria is that whenever the inputs that the instruction needs are available, right? So if I have all my data available and I know what I want to do, how come the instruction cannot be executed, right? How come, right? How come the instruction cannot be executed, right? And the third thing is, well, as long as there's a functional unit available, right? Why doesn't the processor put the instruction in execution, right? If you think carefully, these 3 things are all you need for an instruction to be executed, right? But right now, we put one more constraint, which may not be necessary here, is that we want, we want all instructions to be executed in order, right? So let's examine if this is a possible idea that let's lift that constraint, just having instruction executed out of order. So that's why we come up with this dynamic instruction scheduling out of order execution, right? So this is not a some kind of smiling face. This means out of order. I know this looks fun, right? Okay, so like this is what we need to do whenever to execute an instruction, right? So in theory, what it means that, okay, whenever I decoded an instruction, whenever there is an available functional unit and whenever the data dependency is resolved, right? So one of the most important, so for the decoding thing, right, we know, well, if I decoded a lot of instruction and having them in a queue, and those could be predicted, right? And there's no turbulence there as long as you can continuously fetch in instructions and assume that we have a perfect predictor. So that's not an issue for now, right? And functional units, let's set it aside. So if we ignore these 2 parts, then the most important thing to decide who can be executed is actually the data dependency among your instructions. Agree? So what we are doing now is that, okay, we need to analyze the dependency among your instructions. And of course, the computer has different ways to do it, but as human beings, we have our own ways of figuring that out. And that representation is called data dependency graph. So this slide, I'm giving you an example regarding how to compose that data dependency graph. So for this example, we have 10 instructions. And whenever you have an instruction, and again, right, you want to execute the instruction in order. Well, you want to logically execute the instruction in order. A lot of stuff that you learn in discrete math, there is some kind of order, right? What's the name of that order? Okay, topological order. Yes, I love you. All right, so here's the thing, right? So the topological order, right? So we want to figure that out, right? In this, as long as that order is right, the execution result should be right. So now you know why you need to learn discrete math, right? So we are basically create that kind of graph within this instruction sequence, right? So the first instruction, right, is a move L, RDI, ECX. So you know the target, the output of this instruction is ECX, right? So first of all, we put 1 here, right? That's the very first node. And then for the second instruction is add I for RDI. So it's depending on RDI. But does it have any dependency with 1? No, right? It doesn't rely on the output of instruction 1, right? So you should put it as a separate node on the data dependency graph, right? So now let's look at instruction 3. Does it have any relationship with instruction 1 or 2? Yes, with who? with 1, right, on ECX, right? So let's have an arrow from 1 to 3, meaning that these two instructions, they have a dependency, and a dependency, the direction of the dependency is that 3 is waiting for, 3 will be waiting for the result from 1. So look at 4, is compare RDX and RDI. So does this instruction has dependency with anyone here? 2, right? Because 2 is actually modifying RDI, right? So there is an error between 2 and 4. Okay, how about 5? Is jump not equal? So for this instruction, who do you think it will depending on? Or 4, right? So most of the time we can just looking at the register, but x86 has a thing that is hidden called flag, right? So instruction 4 will actually set a flag, and instruction 5 is going to read it. So it cannot function correctly without having instruction 4 finished, right? So that's another one. How about instruction 6? What is it depending on? 4. Okay, is it depending on 4? So does 4 modifying anything? No, right? So if it's not modifying anything, it doesn't generate a new output, right? So no one will be depending on it, right? But if we track where we modify RDI, when was the last time we modified RDI? 2, right? So actually 6 is depending on 2, right? So there is a very strong implication here, right? So for instruction 3, basically, if we ignore the ordering, right, it could be executed right after instruction 1 finished, right? Instructions 2, it doesn't need instruction 1 to finish, right? It can execute at the same time with instruction 1, right? And instructions 6 and 4, I mean, they can execute together after instruction 2, right? Doesn't have to be depending on 1, right? So if you continue this analysis, right, instruction 7 is also depending on instruction 2. And instruction 8 will be depending on both instruction 6 and 3. And gradually, you can have some analysis regarding their relationship, right? And from this relationship, right, you can pretty much see, okay, these 2, they are a group that can be parallelized, right? These 3, they are a group that can be parallelized, right? And because they only depending on 2, right? And like this is a single one, this is a single one, right? And well, and this 2, they depending on 4 and 7, right? So you can have this kind of analysis and figuring out who and who can be executed together and who cannot be executed together, right? Something like this, right? In theory, that's what we hope, right? So in theory, if I want to completely fill the pipeline, I can basically do like 2 and 1, right? And then 4 and 6, right? Or 4, 6, 7, whatever, right? So in theory, right, if they all use different functional units, I'm supposed to be able to execute all of them together, a lot of them together. Agree? Okay, but let's look at this, right? So assume, so the fact is that, okay, if we can reorder the execution order of our instructions, we should be able to get performance. And we see a lot of them could be reordered from our priori example. But let's calm down and let's imagine that, okay, right now you have unlimited LU and you have completely freedom. You have the complete freedom to reorder your instructions. Then which of the following pair can we reorder without affecting the correctness? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay. Okay, see? So it's great, right? So after the analysis, right, a lot of us are thinking about B as the answer, right? So how do you guys solve this one? Why do you guys agree that B is the answer? Okay. Okay, you look at all options, right? So first of all, right, if you remember 1 and 2, do they have the data dependency in the data dependency graph analysis? Do they have dependency? 1 and 2. Do they have dependency? No, right? Because they are two separate nodes, right? But they don't actually have dependency, right? So if you draw a data dependency graph, as far as I remember, it's 1 and 2, right? And 3, right? And we have 4, 6, 7, right? Who else? I think 9 is depending on 7, right? So 9 is here, and 8 is then depending on 6, right? And 9 is depending on and 10, right? So that's pretty much the data flow graph we have, right? So if you look at the data dependency graph, 1 and 2, they are actually irrelevant here, but we cannot reorder them. Why not? Because if you do that, right, we will have the issue on RDI, right? You are going to modify the value of RDI and the code will become incorrect, right? Okay, how about 3 and 6? For 3 and 6, right, they are not depending on each other, but why can't we reorder them? Why can't we reorder 3 and 6? What's going to be wrong? Yeah, but why? But okay, so forget about the performance, right? Yes. Yeah, so if you move 6 up and it's still 3 later, are you going to get the desired result? The answer is probably not, because the ECX is not the ECX you want, right? Okay, how about 4 and 7? So again, right, if you look at 4 and 7, they don't have dependency with each other, right? But why can we not reorder them? If you execute 4 before 7, what's going to happen? So we are also modifying RDI here, right? How about 6 and 7? So 6 and 7, right? Again, they don't have dependency. But why can't we not reorder them? Same reason, right? Because here 6 depending on RDI, right? And 7 is modifying RDI, right? So here's the thing. Okay, even we have perfect range predictor, even we have the ability to reorder instructions just based on their data flow, there are still issues, right? We cannot reorder them because we have so-called false dependencies. So there are two types of false dependencies. So first of all, why are they calling false dependency? Because they are just not right? They are not true, right? So why they are not true? Because if you come down and look at their relationship, they should not have a dependency, right? I'm not relying on your data, but how come I have to wait for you to finish, right? Because they are using the same name, right? So you got it, right? So, okay, I don't want to raise too much of the the issue here, but yeah, okay. You know, like, okay, the successful rate of, or how much money that you have to pay, well, Okay, so how much money you have to pay for your car insurance is highly related to your zip code, right? And sometimes you will have a feeling like, okay, like if I'm in okay, so my zip code used to be in Pasadena, and now I'm in Mira Mesa, and the biggest change is that every year I got a reduction of $200 for my car insurance, and sometimes you are thinking about like, okay, I'm a good driver, right? I don't contribute to the car accident rate in Pasadena, but why am I paying more, right? Same reason, right? So they are not true. Well, I think that's not a good analogy. Anyway, forget about it. So the thing is that a lot of dependencies that we are being blocked is not because we really depending on the input of another instruction. It's just because we have false dependencies. And for the false dependency, there are two types of false dependency. The first type is called write after read. So a later instruction, it overrides the source of an earlier one. So for example, in instruction 2 and 1, right? Instruction 2 is overriding RDI, which is the one that instruction 1 depends on, right? So in this way, it's right after read, right? Right after read. So that's why. So by right after read, it means the later instruction is writing after the first instruction who is reading, right? That case, this is a false dependency, right? So instruction 2 and 1, 6 and 3, 7 and 4, 7 and 6, they both fall into the category. And another case is that write after write. It means that the later instruction overrides an output of an earlier one. So for example, instruction 6 and instruction 1, they are both writing to ECX, right? So if you move the instruction 6 up, then one of them is going to be gone, right? You can only receive one output and everything going to be wrong, right? So those are two types of false dependencies that prevents us from having complete freedom of reordering our instructions, right? So, and if you look at the reason why we have that issue, as Fang Zhang pointed out, right? It's pretty much someone is overriding the source register of an earlier instruction, right? Or overrides an output register of another instruction, right? So the whole reason is because overwrite, right? And the reason why we have to overwrite is what? We have limited registers. So that also gives you the idea there is some limitation in compiler optimization. So in compiler optimization, if your instruction set architecture only give you 16 registers, then the best you can do is to use that 16 register to optimize your code. So it turns out compiler optimization has no way to avoid false dependencies because they have very limited number of registers that they can use to compile their instructions, right? And the other thing, which is also another limitation of compiler, right? So in the example that we have been showing off, right, is that the compiler has no way to predict branches. So we cannot actually reorder instructions across the boundary of iteration. However, if you are able to predict branches like the hardware can do, when we draw the data flow diagram, right, you can actually see the data flow actually ignore, the data dependency graph actually ignore the boundary of iterations, right? And that's another limitation of compiler. And another limitation which we have seen earlier is that even though we reorder the instruction, however, when we place the same code into a superscalar processor, the way how it works is very limited, right? So compiler has that many limitations. So turns out we have to use hardware to best utilize the available functional units we have. So turns out if we want to eliminate the false dependency, we have to have a hardware mechanism that allows us to give each output a new register so that we can eliminate all false dependencies, right? Because the main reason why we have false dependency is because we have to override a register because we have to reclaim those registers so that we can store new outputs, right? However, if your hardware has the ability to temporarily redirect these outputs to a new place, you can avoid that restriction, right? So imagine this, right? So if today I have the hardware mechanism, can dynamically rewrite my code like this. Okay, so the right-hand side is like an imaginary x86 instruction set architecture, right? So assume whenever I see a new output, I redirect it to somewhere, right? So starting from instruction 2, this is what I can do, right? So for this instruction, I can store my output to a register called T0, right? And then for the rest of the instruction, who depends on RDI, it can be in it has to depend on T0, right? So for example, instruction 4, instead of comparing with RDI, is now comparing against T0, right? So look at this, right? Previously, we said we have trouble reordering instruction 1 and 2, right? However, now, because 2 is putting its output to T0, so even though instruction 1 is depending on RDI, it's not affected. Did you guys see that? Right? So the key is that, okay, if I have a mechanism that allow me to temporarily store my output to other places, then I can potentially eliminate all false dependencies, right? So that mechanism is called register renaming and speculative execution. So these are actually two mechanisms. So by register renaming is the mechanism that we store the outputs to a new register. And speculative execution is actually the fact that because the hardware relying on branch prediction to perform more aggressive optimization in your code execution order. But even though it's close to 100% accuracy, but once a while, you are still going to get it wrong, right? So there is some mechanism that allowed the instruction to be executed, but reserve the capability to retract all the updates of those instructions that we are not 100% for sure that they should be executed, right? So that mechanism is called speculative execution. So these two things put together, that's actually how modern processor would exploit the usage of multiple functional units at the same time. So speculative execution is a way that allow instructions to across branches without facing issues like exceptions or branch mispredictions. So and register renaming is a mechanism that we try to use additional registers to store the outputs. So it turns out this is the new pipeline we have. So previously we have add branch prediction, we have add data forwarding path. We also have split instruction and data cache. But with register renaming, right? These are the new additions. So there are two things that we added here. One is the register renaming logic, which decides where the output should be stored. And for the follow-up instructions, where should they find their source inputs, right? So that's the register renaming logic. So you can imagine this register renaming logic is pretty much doing the job that in one of the slides that I showed before. Whenever there's a new output, I give it a new register name. And whenever a later instruction is depending on that output, I redirect their sources to that new register. So that's the register renaming logic. And there must be a place that I store those renamed instructions before we can schedule them. So that's reorder buffer. And there is another thing we need from the reorder buffer is that because we are not 100% for sure if the branch prediction is correct or not. So reorder buffer is also the place where I would buffer result that is not 100% certain that should be presented to the program, to the user. So that's why we need a buffer, right? Okay, and this is also the place where we can start fetching. We can the rest of the processor pipeline can start fetching instruction. So that's the high level diagram of that. So you can pretty much imagine that register renaming is essentially some kind of hardware that can schedule instructions according to their data dependencies. And for the following figure, most of the time I don't want you to draw it, and but here I show this process is just for you to understand how it actually works. So right now, I kind of like fast forwarded the process, and here I'm assuming that I have a processor with 2 fetch widths and 2 decode widths, and with the ability of renaming 2 instructions at the same time. So you can imagine that every cycle we can, with the help of branch predictor, we can get 2 instructions in a pipeline, and we can decode 2 other instructions and rename 2 other instructions. So I kind of like fast forwarded for the first 3 cycles because they are pretty stable, right? So let's look at the 4th cycle. So if we want to do the 4th cycle, right? Okay, another assumption that I have is that for this processor, I'm assuming that the processor can issue, is a 2-issue processor. So what does that mean by 2-issue? It means that the scheduler is within the processor can select at most 2 instructions into execution. So the criteria of selecting 2 instructions into executions are 2 instructions that do not conflict on the functional units that they need. And also, these 2 instructions, if there are more than 2 instructions that you can execute, earlier should go first, right? So those are the policies that we have to follow here. So right now, at instruction 4, right? At cycle 4, 2 instructions are ready to be executed, renamed, because they are renamed, right? That's instruction 1 and 2. So looking at instruction 1 and 2, do we have anything prevent them from executed together, being executed together? Why not? So what functional units do you think instruction 1 will need? Memory unit, how about the second one? It's an LU, right? So in this processor, we assume for memory, it takes 4 cycles. And for others, it only takes about 1 cycle, right? And okay, so now, since instruction 1 needs memory and instruction 2 needs LU, right? So, and also remember, we have register renaming. So here I'm attaching a small table. The small table has 2 fields. One, the first part is the logical or say architecture register that the processor presents to the rest of the world. And the physical registers are the ones that we can actually use to store our outputs. So what happened is that, okay, right now I have instruction 1 and 2, and this one has ECX as the output, right? So according to our register renaming policy, we need to find a physical register to store this output. So the register renaming logic, so they're saying that we have a set of physical register from P1 to P10. The register renaming logic, obviously we can start from P1, right? So right now we can put keeping that ECX is in P1, and for the second instruction, RDI, right? Let's put it, because it's a different one, right? So we just put it in P2, right? That's where we are. So you can imagine that, okay, for other instruction who depends on ECX, P1 is the place to look for its input. And for other ones who depends on RDI, right, they should go to P2, right? So that's the idea we have now, right? And so far, because we have 2 instructions decoded, so only 2 instructions decoded, so we don't see others can be executed. So at the next cycle, we have 3 and 4. So looking at 3 and 4, who instruction 3 is depending on? So originally it's ECX and EAX, right? But right now this ECX is redirected to P1. Agree? So instruction, so if you look at the table, right, P1 is currently not valid, meaning that I don't have a result for P1. So instruction 3 cannot be executed in the next cycle. Do you guys agree with that? So in the next cycle, right, we have 3 and 4 decoded. So now look at 4. Can we decode instruction 4? Can we execute instruction 4? Yes, right? Because instruction 4 is depending on RDI, which is P2. And if we only take one cycle for LU instruction, right, at that time, it's pretty much done, right? So you can imagine in the next cycle, instruction 1 will proceed with its memory pipeline. And we can execute instruction 4 with data with the help of data forwarding. And instruction 2, because right now we want to maintain an illusion that instructions are still executed in order. And right now, because instruction 1 hasn't finished, so instruction 2 still has to be put into reorder buffer in case there is something wrong in instruction 1, right? So now instruction 2 is putting into this reorder buffer. It's currently buffered, right? But as long as instruction 1 finishes, instruction 2 is ready to retire. So now in the next cycle, now in our queue, we have 3, 5, and 6. Who can be executed? Five is depending on who? 4, right? So at that time, we can see 4 finishes, right? Can we execute 6? Yes, right? Because 6 is right now depending on RDI, which is P2, and P2 is already valid, right? So in the next cycle, and how about 3? Are we able to execute 3? No, because still, right, depending on P1, and P1 is not ready yet, right? So what we can imagine is that in the next cycle, right, what's happened, and one thing that's interesting in this cycle is that you can see 4 is now executing before 3, right? So that's out of order execution, right? So, but what happened in the next cycle, as you guys said, we can execute 5 and 6, right? And in the reorder buffer, because 2 and 4, they are finished, so they are in a reorder buffer. Okay, and later on, next cycle, we have, right now we have 3, 7, and 8 that's in a queue. Who can be executed at this time? Can we execute 7? Yes, right, because 7 is only depending on P2, right? And P2 has been ready long time ago. How about 8? No, why not? Still waiting for P1? It's actually P4, right? So that's another thing that's interesting, right? So right now, even though it looks like instruction 6 and instruction 1, they are the same instance, but because right now its output, their outputs are directing to different physical registers. So their chain are decoupled. Chains are broken, right? Do you feel like you are in a church? Never mind. Okay. And but at this time, instruction 3 still cannot be executed, right? So we have to wait for at least instruction 1 to finish its M4, right? So what happened is that in the next cycle, right, we can put 7 in execution, and in the meantime, 1 and 6, they are also make progress in their memory pipeline. But one thing that you find is that, okay, in the next cycle, right, because instruction 1 is likely to finish, right, if there's no cache miss, right? And that's assume that we have a perfect cache now. So if there is no cache miss, you know instruction 3 can be put into execution, right? And in the meantime, reorder buffer has 2, 4, and 5, and it's all because instruction 1 hasn't finished, right? So now, in the next cycle, finally, we can put 3. But okay, we can pick one more instruction to execute. So we have, who's here? We have A9, 10. So among this instruction, A9, 10, who can be executed? A9, 10, who can be executed? Can A be executed? Can A be executed? No. How about 9? 9 depending on RDX. Someone changing RDX? RDI, who is changing RDI? 7. Has 7 been finished? At that time, at next cycle. Yeah, right? So 3 and 9, right? They can be, well, 3 and, okay. But, okay, we cannot execute 9 still, right? Because we only have one ALU, right? So if we post, so there is actually a structural hazard here because we only have one ALU. So both 3 and 9, 3 is using comparison logic, which is supposed to be ALU as well, right? Because comparison is basically having subtraction, right? And the most significant bit is used as the flag. That's the real implementation. Yes? Well, nobody actually does that. Oh. Okay. So so here's the thing, right? Right now in your reorder buffer, you have 1, 2, 4, 5, 7 that has been ready, right? But you know, because 1 and 2, they can be retired together, right? So in the next cycle, we only see 4 and 5. And 3 is right now in execution. We are supposed to be executing 9. However, because there is already 3 occupying the LU. So unfortunately, 9 can only be executed in the next cycle. But looking at 9, can we execute 8 at the next cycle? Yes or no? Instruction 8, can it be executed in the next cycle? Still waiting for 6, right? How about 10? Can we execute 10? 10 depends on 9. Okay, how about 11? 11 is here, right? Can we execute 11? Waiting for 6? 11 is waiting for RDI. Who? Right? So 11 could be executed, right? 11 could be executed, right? So in the next cycle, we can actually put 11 into execution and 9 can be executed. And because we retire 1 and 2, right? So right now your reorder buffer only have 3, 4, 5, 7, right? And then in the next cycle, 3, 4, 5 can be retired, right? Because all the ones before 5 has been done, right? And now, in the next cycle, we have 8, 10, 12, 13, 14. Who can be executed? So 8 is waiting on who? Okay, so A is waiting on 6, right? So A could be executed, right? And 8 is an LU instruction, right? And it's the earliest one, right? So there's no doubt we can have 8 using this ALU. Now we can pick one more instruction. Who is not using ALU? Can we find that instruction? 10 is not using ALU because it's a branch instruction, right? So A and 10, right? So kind of looks like you guys got it, right? So if you draw this figure, keep drawing, right? This is what it looks like at the end, right? So it takes 15 cycles to have 19 instructions being executed, right? Or if you just look at 15 instructions, right? It actually takes 13 cycles to have all 15 instructions being execution, right? Question? Okay. Okay. So most of the time, this is not what I would imagine you to do, to draw the priori one. That's not what I want you to do, right? Because thinking about the fact, register renaming is effectively trying to mimic, is a hardware mechanism that try to figure out the data flow, data dependency among instructions and schedule, right? And as a human being, you have a better way to look at it, right? A lot of you like graphical representation, me too, right? That's why I like animation. I like to read comics, even better than watching real human beings playing the drama, right? But so what we are going to do here is that we are going to kind of like realign that data dependency graph to see how we can execute the instruction. So here's my trick, right? You have 4 different areas, for example. If you have three different types of LU, right? This is what functional units. This is what you will do. You have an area for instruction queue. You have an area for memory instructions, and you have an area for ALU, and you also have an area for branch instruction, right? So again, assume that we have 2 instructions that are available in the instruction queue, right? You know, the next cycle, you can put 2 instructions into execution. And instruction 1 and 2, right? Do they have dependency on each other? No, right? So for instruction 1, you know this instruction is using memory unit, right? So you put them in the column of memory unit. And instruction 2 is using the LU. So I put it in an LU part. And the next instruction, instruction 3, right? Who is it depending on? Instruction 1. And how long does it take for instruction 1 to generate its output? 4 cycles. So you know the instruction 1 okay. So again, remember our policy. Earliest instruction should be executed first, right? So you know the earliest time instruction 3 could be executed is actually 4 cycles later than instruction 1, right? So let's put an arrow that is 4 cycles later for instruction 3. And instruction 3 is using the LU, right? So let's put it in the LU area. And instruction 4 is depending on instruction 2, which is available right after instruction 2 finishes, right? So let's put it in the next cycle, right? Now we are decoding instruction 6 and 5. And instruction 5 is depending on who? 4, and it's on the branch, right? So it's actually here, right? And instruction 6 is a move instruction depending on RDI. Who generates the RDI? 2, right? So if it's depending on 2, right? Which means at this time, no one is occupying this slot, right? So let's put instruction 6 here, right? Did you guys get it? Right? So now looking at instruction 7, it's depending on RDI, right? And modifying RDI. So which ALU is it using? The ALU, okay. And who is it depending on? Instruction 2, right? So so at the next cycle at this time, is someone occupying this slot? No, right? So we can put it here, right? So this is actually, I think I want to draw this one, right? Okay, so how about instruction 8? It's using ALU, depending on ECX, EAX, right? ECX is generated by instruction 6. So when is the earliest time we can execute instruction 8? 4 cycles later than instruction 3. Sorry, instruction 6, right? And in the meantime, because it's depending on the outcome of instruction 3, right? So you also need an error, right? So if now you kind of like know the philosophy of this one, right? So if you complete this figure, right, you can keep expanding this animation. And turns out it will give you the same result that it takes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, right? 15, 14, 15. So it will give you exactly the same result as the previous one in issuing all the instructions. And another benefit that you can potentially see from this graph is that, did you see this part? Like this 1, 3, 6, 8, 11, 13, 6, 18. Right? So your execution is pretty much defined by this path. Right? So it helps you to identify the critical path of your instruction and also help you to find the regularity of your execution. So if you look at this, right, you can imagine your graph would be duplicated. This part would be duplicated again and again, right? And between these instructions, there are actually 5 other instructions within them, right? So totally 5 instructions, and these 5 instructions on average would take 3 cycles to execute. So your average CPI would be actually 0.6 for these pieces of code. Okay. Right. So this is how you find the critical path of your instructions, and this is how you find the average CPI if the code is going to be repeated several times. All right. So now I have a question for you. A lot of you like linked list. Can you identify who determines the performance in linked list? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay. Almost unanimously pick C. What is C? So C is actually, okay, let's go back and look. C is actually the current equal to current X. Why is that?
Because in the memory system, linked list, they'll just place it to whatever available block. So essentially, like jumping from one block, like some crazy other block.
Okay, so again, right, if you look at these pieces of code, right, we can imagine there aren't that many instructions to implement this one, right? So thinking about this, right, how many instructions do you need to implement this one? one instruction. And what type of instruction is that? It's an ALU instruction, right? Very quick. How about this one? Memory operation, right? Because what you actually need is that I need to use current, which is a pointer, as the base address to access the next element, which may be next to current, right? So there may be something like RDI +8 as my input address, right? And then move that to current, right? So RDI is something like that, right? So it's a memory operation. And so it's one memory operation and how many cycles it takes on average. So, right, a lot of you know, right, for modern processors, probably 4 or more, right? So that's a lot. How about this while? It's a branch instruction. How expensive is a branch? So previously, right, if you don't have branch prediction, as I show you in the demo, it will be 30-ish cycles. But now, like this piece is a code, right? If we can assume that we have a perfect branch predictor, although most of the cases it's not, right? But if we have a perfect branch predictor, then and another thing, right? If your linked list is long enough, right? This one should be always correct, right? So for these cases, right? This one is not going to take a lot of time, right? Because all you need to see is if this is equal to 0 or not. Very fast comparison. So I would say maybe there are 2 instructions, one for comparison, the other for branch, right? But because they are fast, right? So they are probably 1 each, right? So none of them is longer than this 4 cycle instruction, right? So turns out the answer would be C, as you guys imagine, right? So, and if you want, you can also draw the data flow diagram. And in fact, this is the implementation of this instruction, as we mentioned, right? I didn't look at the answer, right? But as we mentioned, indeed, it's using RDI, miracle, right? So we have a move instruction, we have an add L, we have a test Q, which is a comparison, and also a J and E, right? So 4 instructions in total. And if you draw a data dependency graph, this is pretty much like it, right? And in fact, there's a clear critical path showing up in the figure, right? This one, right? And if you look at who is 1, who is 5, who is 9, right? 1 is the move Q, 5 is the move Q, 9 is the move Q, right? So it's all, and this instruction is effectively implement current equal to current next. Okay, so now follow-up question. If I have, oops, I forgot to copy the timer. But if I have this, right, data flow graph, data dependency graph draw like this, right? You can trust me. And with this, what do you imagine CPI of this pieces of code would be? What's the CPI? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay. All right. Looks like we need some discussion, right? So go ahead and discuss with your friend for another 90 seconds. Okay. Looks like I keep forgetting the timer. All right. Discuss. Noise. Make noise. Are you okay? Are you okay? Are you okay? Because he looks like he wants to discuss with you. You are too devoted. All right, let's wrap up in 15 seconds. You got it? How do you know that you guys got it? Maybe you are both wrong. All right. All right. 5, 4, 3, 2, 1. Time is up. Okay. After discussion, we see some changes, right? A lot of you are thinking now is C, magic. What do you think?
It's C.
It's C. What is C?
We are thinking that like the part like 5, 3, 10, 4. That
Mhm.
part is like actually the one that's like repeating the central case.
Right, this part, right? So you say 5, 3, 10, 4, right?
But like since it also requires 2 additional cycles to get to 9, so that
Mhm.
means like you repeat every 4 cycles. And
Right.
it's 4 instructions.
Right. And another thing is that, right, this is the critical path, agree? And 1, 5, 9, 13, right?
Yeah.
So it's 4 instructions ahead. And every time you take 4 cycles, it's queued all instructions between them, right? So turns out it takes 4 cycles to execute 4 instructions on each iterations, right? So turns out the CPI is going to be 1.
You got it right.
Okay, okay, you guys got it right. Brandon?
So I got the same answer, but I'm wondering if I'm something wrong. So I got 7 divided by 7. So I was thinking of, we have these basic like blocks, right?
Mm-hmm.
And instead of where you drew,
Mm-hmm.
I go all the way to the start, and we have 7 kind of
Okay, so
instructions.
interestingly, so typically I won't count the starting part because you have a process of ramping up your execution, right? So if I would you, I would try to observe who would be the mature part, right? And if you look at the mature part, it's pretty much like this, right? So it's 4 instructions in 4 cycles, right? So that's how you get a CPI of very complex processors, right? Never try to draw a pipeline diagram because it's not going to work well, right? Data flow graph, this is easy. Well, easier, right? As long as you learn your discrete math, right? Now you guys hate discrete math, right? I know it's one of the, yeah, it's okay. Discrete math is actually okay, better than linear algebra for me. But anyway, yeah. So this is how we get the performance, right? And well, you might think, okay, how far away? Because we are very far away from the textbook now, right? You guys read the textbook, right? But you also notice that I never talk about the 5-stage pipeline that has been listed in the textbook. And what kind of pipeline does the professor tell me, right? I want to tell you, I'm actually giving you something that is very similar to the pipeline of modern processors. So this is the Intel Alder Lake processor. So if you are in 140L, 142L, this is exactly the same processor that you are using. So this is the pipeline of the performance core on these processors, right? So with this processor, you can read most of it now, right? So we have an instruction cache, we have a branch prediction unit, we have micro op cache, and then micro op queue, right? That's the reorder buffer, right? And well, that's not a reorder buffer, sorry. Well, that's the instruction queue, right? And then they have the renaming logic, they have the scheduler, right? So you now know what is the renaming logic, right? And then the scheduler would pick instructions into execution. And as you can see for this pipeline, they have 5 ports connect to the integer LUs. So they can issue 5 integer instructions at the same time. And also here, 5 LU instructions at the same time. And here they have 7 ports for the memory operations. So they can issue 7 instructions in memory. So what you can imagine is that if you have a good mix of instruction, and if they don't have data dependency at all, by default, you can actually execute 12 instructions at the same cycle. And if you can actually issue 12 instructions at the same cycle, every cycle, then you are having a CPI that is 1/12. But you know it's not possible, right? And for integer instruction, if I only have an integer instruction, then my CPI will be 1/5 in the most optimal case. And if it's all memory instruction, it will be 1/7 in the most optimal case, right? And if it's a branch instruction, it will be 2. If you observe carefully, there are 2 branch units. Where are they? There are 2 branch units here, right? So 2 of the ones, they have the branch units, right? So 2 branch instructions at most, right? So that's what kind of processor we are dealing with now, right? But compare against the example that we are having, it's actually pretty rich, right? But again, right? But let's show you a demo. Previously, we just showed a linked list, right? And you know that linked list, okay, my CPI is, right? And you might wonder, okay, for this CPI equal to 1, and given that, right, Professor, you just told me that my modern processor has very good ILP, right, instruction level parallelism. How good is the CPI? So now I'm showing you 2 pieces of code. Oh, hello. Okay, so I have 2 pieces of code, right? So these 2 pieces of code are actually, wait. Okay, let me stop and restart. You know, sometimes if you have trouble with your Jupyter notebook, restart is the best way. Well, sometimes it's depending on your browser. Okay, so it's now good, right? So this is the pieces of code I have. The left-hand side is an array, and the right-hand side is a list. And both of it should have the same length if I design correctly. I don't know how good my coding is, but that's what I designed it to be. But the right-hand side is pretty much like the code that I show you. So you can know like this piece of code is counting how many nodes we have in a linked list. And the left-hand side is traversing every element in the array. So suppose the linked list should be faster because you might traverse fewer nodes if we don't use all of them in the array. And for the array, I just keep traverse everyone. And here I try to create a code and I try to run them, right? And both of them shows, okay, the same depth. Boom, my coding is correct, right? But let's look at how fast in executing them. So for this processor, this is essentially an 13th generation Core i7 processor. So some performance counter doesn't work very well. However, one thing you can find is that the CPI of the linked list, which is the lower one, actually has 2, which is pretty bad. However, if you don't use linked list, it's only 0.4, right? Pretty pretty good comparing against linked list, right? So in a lot of cases, we don't like, you guys want like fancy data structures, but this is an example. If your data structure like linked list cannot fully exploit the parallel functional units within your microprocessor, the performance is going to be sucks, right? Okay, so before you leave the classroom, a few things I want to let you know. So last reading quiz due this Wednesday before the lecture, which is tomorrow, and assignment 4 is up and due this Sunday. All right. Other than that, enjoy the rest of your day. I will see you tomorrow.
Life is a song that you sing, happy or sad, bitter.